How's everybody doing? So are there questions? Anybody have burning questions about, yeah?
So on the substitution and elimination worksheet, I just have a question about the enantiomeric excess.
Uh-huh.
I don't know where to start. I found like one of the old worksheets, but it talked about like temperature and stuff, and so I was putting temperature down. I started working, but I don't know.
So there you want to look at, you've got hydroxide and you're going to go. That's not, this is a very professorial thing to do. You ask one question and I answer another. There's a debate tonight. That's a good debate technique, right? Whatever question they ask, you answer the question you wish was asked. Good debate technique, good dating technique. Right, no, actually I'm sorry, it's a crappy dating technique. It's like just standard marriage, standard operating procedure for marriage. Whatever gets asked. I assume she doesn't watch my lectures. She's probably got better things to do. All right, so the question was, I may get this, distracted myself with all my stupid jokes. Tell you what, I'm going to. I don't like giving you exactly the. Actually, you don't even need the H3O plus. Let's just put it in water. Okay, so this will, I promise, eventually answer your question. Give me the product of this reaction and what the mechanism is. Yeah, the product and the E. Product. If you have number one, try, or if you have the top one, try the bottom. Same question. What's the mechanism on the top? It's not E. It's SN1. 1 is right. So again, you got a leaving group, got a chloride. You don't have a strong acid, or sorry, you don't have a strong base or a good nucleophile, right? Water's all that's there. Water is a weak nucleophile, weak base. Importantly, the chloride is on a tertiary carbon. Right, so tertiary chloride, you don't have a good nucleophile or a strong base. So can't do SN2, right? So this carbon's tertiary, the leaving group's on a tertiary carbon, so there's no SN2. You're also not going to do SN2 because there's no strong base. So this is going to be SN1. The product then will be OH is going to, when water is the weak nucleophile, OH winds up substituting in, not H2O. H2O does wind up in there, but that proton gets taken off at the end. So what's the percent EE? Start at 97% EE. Does it matter what we start with? So the SN1 mechanism, right? That chloride's going to leave. This is equilibrium. That's your intermediate. What's the EE of that intermediate? Doesn't have one. It's not chiral. So I would have accepted zero. I'm glad that's why you were looking confused. Yeah, you guys as a group looked pretty confused on that. Doesn't have one, right? That is not a chiral molecule. There's no chiral center. The carbon that was a chiral center has been rendered planar. Okay? So now water, I'm just going to go ahead and go through this whole mechanism, I guess. Water does attack that carbocation. Carbocations are strong Lewis acids. So water, being a weak nucleophile, weak base, can react with a strong acid. And this is going to give us, again, you'll get, by not showing wedges and dashes here, I'm saying it's 50-50 either direction, right? The water can come into this flat carbon, if the carbon is in the plane of the board, so the water can come here or it can come from behind. So half the molecules would have a dashed methyl and a wedged OH, and half would have a wedged methyl and a dashed OH. So here, bring that. This is another case where the reaction's being run in water, right? This is not strongly acidic or basic. We make a strong acid by having, so we've got a strong acid. And it's hard to get, I don't know, I found when I was in your seat, I found it hard to get this internalized. That carbocation is a strong acid. So you can't have a strong acid. You're not going to have hydroxide attack here. You may want an OH in there, but hydroxide would be a strong acid. So this is what I said over here, right? You're not going to have hydroxide and a carbocation. You'll have water, which is a weak base, and then another molecule of water can take that acidic proton to give us our product. But the percent EE here will be 0% EE, right? It's racemic. Sorry about that. Anybody got you don't have to give me your answer. Has anyone worked the bottom one? A few people have worked the bottom one. Okay. Now I'm going to ask for, what's the mechanism on the bottom? It's SN2. All right, we got a leaving group. The leaving group is on a secondary carbon. So SN2 is possible. Right? Secondary alkyl halide, a secondary leaving group is going to be the slowest possible SN2. You do have a good nucleophile there. SH minus is a good nucleophile. It's not a particularly strong base, but it's a good nucleophile. And then again, the temperature is low. That's going to favor substitution. So all this adds up to tell us that this is going to be SN2. So what's the EE of the product? It's 97. So functionally, there's only two possible answers that make sense on these questions, right? If I ask for a particular EE, it's either going to be 0 because you go through a carbocation and it's going to be racemic, or it's going to be whatever the EE was here. I'm going to say more about that in a second, but for right now you should stick that in your head, that this will give us inversion. So SN2 inverts every chiral center. Okay, so SH comes in there, inverts that chloride. Yep.
And then, so do we have to know, like, in the textbook, there was like an exception where it said, like, typically on a substitution, it'll favor slightly inversion or retention of steering centers?
It will. The only way to get retention is to do 2 SN2s. Right. So this top one is not retention. This wouldn't be retention. This is inversion. Or, sorry, no. This is just racemization. Right. You get an equal mix of attack from the top and bottom. If you can find, I'd like to see what your. We should clarify that. The bottom. And so this is what I was going to say. A pure SN2. If every product is formed by an SN2 reaction, then every chiral center gets inverted. 97% EE, most of the chiral centers, 98.5% of the chiral centers have the chloride back. They get inverted, we'll have the SH out. The 1.5% that has the chloride out, the SH will come from the back and the SH will end up back. So the EE will end up the same. Now, I think what you might be getting at is what I was going to talk about. There are, like this case right here, it's a secondary chloride, so SN2 is pretty slow. If we instead come in here with water, right? So protic solvents accelerate SN1 reactions, they decelerate SN2 reactions. What you might find here is that we start with 97% EE in the chloride, but not every reaction. SN2 winds up being the dominant reaction pathway, but it's not the only reaction pathway. Some of that's going through SN1. And so you might come over here and find that your product is 71% EE, for example, right? If you did that, so if I took my 97% EE chloride and I do what I think is an SN2 reaction and I find that I get a 71% EE, what's happened is 20 or 30% of the molecules have gone through an SN1 path. Right, where chloride would leave, you get a secondary cation, and then that gets attacked. So what you will find, and this does happen a fair amount, right, as we increase the temperature, or if I do things that accelerate SN1 at the expense of SN2, I'll find a lower EE. So if I did this reaction in water and I lost EE, I'd probably go and try an aprotic solvent. Maybe I would cool it down. All right, there's a lot of tricks you can play. Did you find it?
It made me clear my cache, I'm almost there.
Okay. All right, did that make sense? I mean, that would be an explanation for it, but I couldn't ask you that. I couldn't say, you know, if I did this, I could ask for an EE where it's 0, right? It's purely SN1. This reaction here, you don't have a good nucleophile. It's a tertiary carbon. It can't be SN2, so it has to be an SN1. That will be a 0% EE. If you do a pure SN2, I can ask you the E if I give you the E. If it's going to be 71%, I can't ask you like, what exact EE will it be? I might be able to say, do you think the E will be the same or go down or increase? But there's no way to just know looking at a reaction how much. You might know that some SN1 is going to happen, but not how much. So if I'm asking for a number, right, the only way to predict that ahead of time would be 0 or the same. Got it? Brendan?
I don't know where the chart was.
Okay, so
There's a chart that described that.
I tell you what, we haven't been using this much, right? Boy, I hope we haven't. It wasn't getting used much, so I stopped paying attention to the discussion on the Canvas site. Anybody posted anything there in a while? There's probably Do you have it?
Yeah,
Oh.
so under the SN1, it says for the stereochemical outcome, the nucleophile replaces the leaving group to give a nearly very Smith mixture. In practice, there is generally a slight preference for inversion over retention of configuration. Do we need to like mention that?
No, that's good. I didn't remember it in Klein. Anybody else want to hear this? Tell you what, it's 1:45. You guys can go. I'm going to answer your question. Basically what happens, so here, think about what happens, and the fact that there's solvent in here, we usually don't think about this. So, the first thing that happens, right, the chloride leaves. Well, it leaves, but it's still, right, so if I'm standing here and my arm detaches, I don't know, I watched too many bad movies as a kid, right? Immediately, right after that, my arm's going to be to my right. Like for it to reattach on my left, I would have to turn around, it would have to move. So the chloride leaves, and immediately you have what's called a caged ion pair. So you've got the chloride, you've got your cation, but they're surrounded by solvent. And they're in the same relative orientation. The chloride can come back on, or, at this point, the chloride is sitting there blocking anything from attacking this positive carbon. So solvent, if it's going to attack, will come from this way. Generally speaking, it's almost impossible to figure that, and people have argued the SN2 might actually happen that way, right? That the group comes off under the influence of the nucleophile, and then the nucleophile can attack. You can't tell, right? If it's inversion, the short answer to your question is no. I'm not going to ask you anything about that. I might ask. You might need to be able to explain this, right? That the E went down a little bit. Why would that be? And the reason it would be is some of the reaction went SN1, some went SN2. But that whole cage thing is way more sophisticated. The whole issue of solvent, honestly, is massively complex. And in most computational chemistry now, like most theoretical chemistry, we started trying to take it into account, but it is really what the solvent's doing and how it's interacting with reacting molecules is much deeper level. But yeah.